All right, thank you very much everyone for coming. I guess just some points of admin before we get going. So apologies for the cancellation of the previous seminar. That was due to the strikes. I hope that everybody found out about that and nobody turned up to the room. And the next seminar is week commencing the 19th of April. It's Julia Brechtschneider. And I think there's going to be there's 3 more, including that one this year. We are very fortunate to have Daniel Williamson with us today from Exeter, and he's going to talk about uncertainty quantification. And rather than listening to me, I think I'll let you introduce it. Thank you so much for coming.
Thank you. Hi. So let me first assure you that I didn't look up the room and get some pictures and then match my slide theme to the room. This is Exeter's new branding, so that's why the slides are all this colour. So I'm Associate Professor of Stats in the Maths Department at Exeter, and I've spent most of my career working on UQ and particularly UQ for climate type problems, and some theory as well. And then the pandemic happened, and I don't know how many people got involved with RAMP in any kind of way. There's some hands, yeah. So kind of when the pandemic started, there were these sort of emails to anyone who had any kind of funding from the Research Council saying, we need, if you can do anything, tell us what you do, and try and sort it all out. And it just so happened I was already co-supervising a master's student with Leon Dan, who ended up, who is an epidemiologist who ended up working on a sort of SPI-M SAGE thing. And so we ended up involved in the melee of modelling. So anyway, let's give the story. Pay attention to the title, because what this isn't is UQ was really useful in COVID, despite all the things that I'll say at the start. Okay, so models and supporting policy and COVID. If you were in the UK during the pandemic, this picture should be very familiar, need no explanations. This is our Chief Medical Officer, Chris Whitty, and he's giving a briefing at Downing Street. This was live on television basically every night for certain periods of the pandemic, or weekly. And on the screen are cases, deaths, hospitalisations, what's happening now, and also what we predict to happen going forward, in order to explain to the public why whatever measures that were either being announced or being taken at the time, lockdowns and so forth, why they were happening. Okay, so how did all of this kind of work? Well, COVID became a thing, and let's not get into the politics of mistakes that were made right at the start, but this independent body called SAGE was set up, containing not just epidemiologists but scientists from a variety of things like behavioural change and so forth, to sort of advise government. SPI-M, which is the body that I engaged with, was the modelling group, and so a collection of epidemiologists with their own models all ready to go, somehow calibrated to early data on COVID, were being used to provide what's happening now and what's going to happen if we carry on, and what might happen if we intervene in some sense. Lockdown being a big one, but there are lots of other interventions that were posed. Now, a very important thing about the pandemic was that the turnaround time was short. So what would happen, particularly in busy periods like when Delta was emerging or Omicron was emerging or pre-lockdown, the policymakers would pose a question maybe on the previous week, like on the Thursday or the Friday. We would have an early look at the data on Thursday, the data would refresh on Monday. SPI-M met on Tuesday morning, well, about 11:30. They met SAGE the next day. SAGE papers were due Thursday, and COBRA or whatever interaction SAGE had with government would be happening Thursday, Friday, and that's why a lot of the announcements came on Fridays, apart from some of the really, really big ones where things were being So if you're a data scientist working on this problem, your model better be ready to go. And then on Monday, you've got, well, not quite 24 hours, sometimes 24 hours, sometimes about 18 hours, to do a thing and provide something to SPI-M. Everyone would do that. And then SPI-M would provide some certain summaries to Sage and so on. So I, of course, never spoke to Sage if there were these layers, but that was what was going on. Okay, so I'll tell you a little bit about one of the models. This is the one that we're going to work with, but there were a few in SPI-M. So it's called MetaWards. You can go and download it and play with it and do whatever you want. Basically, it's SEIR. I'll come to what that means and what it looks like for our model in a minute. But it's spatial, so it divides the country into these tiny little units called electoral wards. So everyone has their own MP in one of these wards, right? Well, in fact, collections of them have MPs, right? So there's 8,000 of those, and there's fewer than MPs. From the census and so forth, they know where you live and where you work, so that travel is built into the model for everybody, and they know where people go and play through things like Facebook and other stuff, so that kind of travel is built in, and so connections between place happen through those sort of underlying data sets and the parameters of this particular disease. And well, that's all I want to say here. This is our version of MetaWards. You can go and make your own, and the very main thing to say about this, I'll explain what it is, and then we'll explain the modelling framework idea. So first, S, if you don't know your epidemiology basics, stands for the susceptibles, so that's everyone at the start of a pandemic. If you're exposed, you enter this class. It takes one time step to move a compartment in these kinds of models. So you're exposed. At some point, having been exposed, you become infectious. So that's all of these classes here. In our particular model, we had a class for asymptomatics because there was a lot of chat about asymptomatics wandering around, not knowing they've got COVID but infecting people. And then there's the pre-symptomatic, so you're now infecting people but you're not sick, and then you get sick. And then there are three kind of paths out of being sick. Either you sort of just get a little bit less sick and then recover, you die in the community, or you move to hospital and then you might recover or die in hospital. And a previous version of this, we added a compartment for intensive care, back when we were trying to work out how many ventilators are we going to need, what's the bed situation, we're building Nightingale-type hospitals. These models are not set as, this is my model, this is the structure, that's it. They're frameworks. So when you have an idea like, how is it going to be when we open up universities in September, new compartments arise, you apply it in a different space, there are different parameters for how students might engage compared to how populations might interact, particularly because they're doing so in universities and things are tighter. So it's a modelling framework, and that is the challenge that I didn't really realise when I got into this. So when I worked on climate, the model is fixed. It gets locked down at some point before the IPCC cycle, and then you can do all of your UQ on. In COVID world, the problem's issued on Thursday, the modelling is happening right up until Monday, and then you've got 1 day, or less than 1 day. Okay. This is what a simulation would look like. In fact, this is half. This is a tiny fraction of the simulation. So this would be this was the max number of infected people, so the max number in here over a very short time period. And I'm only showing it so you can see just how high the resolution is of this kind of model. So there's a lot going on. To run it, you need to run it on a supercomputer at this level. If you want slightly bigger spatial aggregations, so the one we'll look at later has local area districts, for about 300 of those. You can run that, well, we still run that on a supercomputer because it takes forever to do ensembles, but I mean, you can run it on your laptop a few times. Okay. So stepping back, that's the COVID problem, that's the world that SPI-M is living in, the researchers on SPI-M are living in, and the uncertainty from all of these models is not just being shown to policymakers, of course it is, and then they're deciding things that affect everybody profoundly. And then they're showing it to everybody in these sort of nightly TV reviews. So with the sort of quantification of uncertainty to aid decision making is something that we felt, we watched on TV. So how is it done? Well, in UQ, which is my area, the basics look like this. If you're not a mathematician or a statistician, any really technical slides, this isn't one, bad news, but any really technical slides are there so you can look at them later. I will breeze over the maths if it's a bit too much. So, calibration or a general UQ framework looks like this. I'm interested in some physical process. Why? For COVID, that might be the state of COVID. So who's in all of the different classes at any particular time, at any particular location in space, maybe all of the locations in space, and maybe across all of the age groups. Whatever. So I'm interested in that. That's the process. I get some look at that process, some observations, but I don't see all of it. I see some aggregations, maybe I'll just see deaths and cases and hospitalisations. And each of those aggregations, so the W is doing some sort of aggregation and masking for the things of Y that I can see. And I've got some error on those things, and each of those different things I will see have different types of error depending on the way that the data was collected. And then I have some computer model for Y. We just talked about that thing that runs on a supercomputer, and it's some function of some parameters. For meta-wards, the parameters are things like R0 and the time one spends infecting other people without having symptoms and other things like that, and also slightly nebulous parameters that have meaning in terms of the rate of spatial transmission and the amount of travel that happens and so forth. But so there's a complex set of these parameters. And the UQ problem is, well, how informative is F for this, for the reality, and what should the parameters be? And I put this last note in here. So if F was just a statistical model, I'm just describing statistics, right? So that's parameter inference 101. I describe the world with a model. I infer the parameters using, well, I'm a Bayesian, so Bayes or maximum likelihood or whatever it is that you like to do. What makes UQ slightly different is that F is not usually a statistical model. It could be stochastic in some sense, but it's actually a process model. So there are things from, I want to say physics, and I'm using that as a term to mean that sort of people have modeled the real world in various different ways. And there are things that they haven't modeled. Now every model is different. Our COVID model didn't have schools. Our COVID model didn't have care homes. That's going to be important later. So when things are missing that are going to affect Y, there is something around called model discrepancy that you have to account for. I'll give a slide in a second. Or your parameter inference is nonsense. And then the other thing is that most statistical models, we can run them thousands and thousands of times in MCMC or some sort of optimization to get the parameters, and you can't do that with these complex models. They're very slow, and so we use these things called emulators. I'll come to those in a second. So these two big UQ ideas that we think everybody who's ever used a model to learn about anything should know about and use in order to do UQ. We came to the table at RAMP with these things, so like we can do these for you. So a little bit of the technical stuff now. If you want to calibrate your model, you link it to reality by adding a discrepancy. So reality here, the C is some control parameters, like if I lock down, what will be the new interaction rate in some sense. And you can play around with C. And you say that that's the model at its best parameters, the ones I'm trying to figure out, so like the true R0 and the sort of true average time it takes to start infecting other people, plus a discrepancy term that's independent of the model. Okay, and then there are two sort of big approaches. One uses a Gaussian process on the discrepancy term that requires this variance construction, and then you put a prior on the thetas and you can infer the posterior. I won't give the maths of that inference, but it's a Bayesian calculation you can do. And the one that I've usually done for various reasons has all the same ingredients without this prior, and aims to cut out the regions of this particular space, the space that theta lives in, that couldn't contain theta star. And it does that by looking at a distance. So what this I you'll recognize hopefully is a Mahalanobis distance, or like a standardized distance. If this thing is small, either the model is close to the data, win, or the uncertainty on the difference between the model and the data is so big that I can't really say anything. So because those are the two possibilities, we cut everything out where the distance is big, because we're sure that it's bad, and everything else is not ruled out yet, and there's a sort of set of parameters that are left where this thing exceeds a threshold. And then hopefully your goal is to reduce the uncertainty by running experiments as much as possible so that you become sure that everything's good, in a nutshell. So, a note on what happens if you don't have discrepancy. There are lots of papers like this. This is a slide after with references for later. But basically the consensus is your parameter inference is worth nothing. Like even in the simplest of models, if you don't have that discrepancy, the truth will be over here. You'll be very sure that it's over here. You'll be wrong, and all of your future projections will look terrible. So there's a whole nice set of literature on this, including a paper by John there. It's nice to even know it's left. Maybe I shouldn't have put a paper by John here. Moving on. So that's discrepancy. That's the first thing that we thought we were going to bring to the table. The second was emulation. So Leon's like, well, I can only run a few simulations on my supercomputer. And how am I going to get uncertainty out of just a few simulations? And we're like, oh, we can build these emulators, and they're going to sort of super speed the model. And the idea behind emulation is to say, well, f itself is an unknown function. I can choose some thetas and run it, and that gives me data on that unknown function. And then I can use a statistical model for functions. The Gaussian process is this one. There's deep Gaussian processes now that everybody's into. Another one. And we can essentially infer this function by updating a prior distribution for the points that we've seen. I'm going to show you what this looks like, because I think it's better than it's science kind of talk. So over here I have this true function is the orange triangles. It's non-stationary, which means that it's sort of this kind of smooth over here and this kind of smooth over here, but then there's a spike, which is difficult to model for a standard GP. I observe the function at 5 different points. Oops, that's 5 different points. And my emulator has a mean and, well, a 95% credible interval on the prediction of the function, or a variance, and that's 2 standard errors, whichever way you want to view it. So with only 5 runs of a function, particularly one that's non-stationary in this kind of way, you can see by this emulator's garbage. We add another 5 points. It gets a bit better, the uncertainty is kind of big and it's missing the spike. Add another 5, it gets a bit better. And add another 5, and this is kind of what most people would call okay, even though it's not capturing this smooth thing very well. It's too uncertain down here, it's too uncertain over here, and it misses over here. That's kind of the limit of stationary GPs. And the reason everyone's obsessed with deep Gaussian processes is because when you do the same sort of thing, it learns how to amend the kernel so that you can get around these changes in smoothness as you move across a function. All this is fitted in an R package you can nicely download that's linked at the end if you want to play with deep Gaussian processes. But we'll move on. So we have these nice sets of tools. Discrepancy that we can think about, we can help you put that in and calibrate with discrepancy, and emulators to help you do it in reality. So, UQ for COVID. This was my project that was funded. So we have all the ingredients when working with SPI-M, delivering to policymakers, of a really good UQ problem. So models that are wrong, in various ways that we kind of understand. Like that picture of MetaWards I showed you, did you notice it didn't have Scotland? It doesn't have Scotland. So people can't go to Scotland, and moreover people can't come from Scotland to infect us. There are no aeroplanes, so there's no way of infection getting in. It's a model. That's fine. So we have an imperfect model. It takes all night to run on a supercomputer, discretization, and the uncertainty is, well, it's life or death. I mean, those bands will be all that a decision maker sees. Are they too wide? Are they not wide enough? If they're not wide enough, and you make a decision based on that, does that mean loads more people die? That seems quite a big deal to me. If they're too wide, are we staying in for an extra month? Seems a bit... So it's important. Okay. UQ wasn't used at all, despite me being funded to do it partway through the pandemic. Nobody used it. Now that's not to say they didn't quantify uncertainty in other ways, and there's no criticism of anyone on SPI-M in this talk. Please don't construe it as that. This is more a criticism of mine, and certainly my field's misguidedness is one word, arrogance is another. Okay, so we started working with SPI-M back in May just through RAMP, and what we did was we thought, okay, we're going to do a UQ, how are we going to do it? So we developed all the architecture that you need, like running a model for one simulation and running a batch of simulations to build an emulator are two completely different things if you've ever done it. There's a month lead time normally just setting up those systems so that everything works. Modelers tend to write scripts, a whole script just to run the model once, and you want to run a script to run the model 10 times with different settings. It's a lot of work for someone to figure out. So where does the model run? How did we store it? And because it was RAMP and because it was COVID, anything we wanted you could have. So Jasmine is where they store all of the climate models, and it costs a lot of money. That's free. The supercomputer time, that was free. So it was really cool everybody was trying to help. And we developed a nice proof of concept. We emulated MetaWords up to about, by the end, I think it was by the end of June, so we'd all come out of that. We'd all sort of come out and we were allowed to meet 2 or 3 friends in the street and so on for coffee by then. We showed that we could calibrate the models, and then we submitted a grant in July to say, okay, as the pandemic moves into its next phase, which we imagined we're going to need local lockdowns for the winter, a vaccine will probably come soon, we're going to work out how to help distribute that, and variants will come along, because we're working with the epidemiologists, we're not clairvoyant, they know how these things work, so all of these things that did happen, I didn't predict, but the people I was working with and wrote the grant said that's what we're going to have to do as we move along. Interestingly, one of the reviewers says, oh, there'll never be a vaccine in time for you to help guide its distribution. By the time the bureaucracy was over and it was funded, they bloody started distributing it already. we weren't even involved in that. So we started, as I say, like that was about mid-December, we kicked off. So, we start. And we're running the full simulator, and we're running up to lockdown, the first one, because what you have to do in order to be able to say anything about what's going to come next is you need to get the MetaWorld state vector to kind of look like COVID does now. So have we got the recovereds right? Because that affects how many people are going to be susceptible to the next thing. All the different age classes need to be right and so forth. So we thought, well, we're going to calibrate, figure out these parameters and move forward. So here we've got hospitalisations versus deaths, and this is coloured by R0. And this window here is where the data was at the time with all of the uncertainty. So the idea is if the dot lives in here, that's a model that's consistent with the data, and everything else would be thrown out. So you see this as someone that does UQ and you're delighted because you think, well, actually, most of this parameter space is not good. That means that I'm going to get a nice tight calibration on my parameters, and this is going to be easy. Looking a bit deeper, so that was nationwide deaths and hospitalisations. If we go regionally and we colour all the ones that were in that Goldilocks zone, in that box green, you can see that we're kind of getting the deaths right on average. So the green ones are near the data, the black dots here are the data, the grey are the rest of the models that aren't very good, and the green are sort of these Goldilocks zone models. And we're pretty happy until we saw this plot. And this plot was kind of the death knell actually for the project, the project as we envisaged it. We did other things instead. And what this plot shows is that the proportion of deaths by region So there are no green dots that get anywhere close to what's going on in London. Something's going on in London, where in the real data, London's taking off, and everywhere else kind of isn't. And so the dynamics in the simulation are, you can see by the green, everywhere, London's ahead, and there's more people in London, it's denser and so forth, but everywhere's bubbling up. And in reality, London was off, and everywhere else hadn't really got going. And we tried for months to sort this out. With every UQ trick I knew and so forth, and the model can't do it. And it's probably because it's missing care homes, and it's also missing the mechanism of certain local authorities putting patients back into care homes untested, which affected London. It's also missing mechanisms such as people coming in. So the way that these simulations are started is you go back to January or February and you put one infection somewhere in the model and then it all goes. But of course that's not what happened, is it? Maybe one infection came over on a plane, but maybe that was lots of infections because they got infected on the plane. And maybe lots of other planes came over the days and lots of other things happened that we don't know about and that aren't in the model. There's just one new person comes in and we just could not get this thing to work. This is a time series of the data. In fact, we're only going up to the middle of March here. That data I showed you was up to lockdown. And you can see this is the real data. London is already taking off, and it doesn't start first. So like in the southeast we have a few deaths, but it never really gets going. Just something ignites London, and it's not in the model. I know it's not in the model because we tried everything. So, the problem with COVID modelling is that if you get the state vector wrong at the start, because you've got exponential growth, particularly in highly populated areas, you can quickly get off track. So even if the parameters are right, and you've got the disease right, and you know everything, if you start it off in the wrong place, it goes off to the wrong place, which isn't very good if you want to work out where COVID is, where might respond well to a local lockdown, where might respond well to an extra testing program if you're hunting for a variant, and so on. It's the same problem in numerical weather prediction, and the way they handle it is via something called data assimilation. I don't know if you've heard of data assimilation, maybe you've heard of particle filtering, which is very closely related to cousin. And the idea is, in weather forecasting, I mean the parameters are fixed anyway, so they're not interested in parameter inference there. The weather's got this whole thing about, a butterfly flaps its wings over here, there's a typhoon in Japan, so you can only ever get things right broadly, but we have these mass data networks. So what you do is you start the simulation off and you keep pulling it towards the data, and there's loads of data in weather. And then you pull it to the last day, hours worth of observations that you have. And I'm not just talking about temperature, rainfall, we're talking about pressure and satellite data and all kinds of products. And then you let it go, and currently the models can do okay for about 2 weeks. The way that it happens in weather forecasting is schematically like this, right? So you have a bunch of different initial conditions of the model, and you run them all forward, and that gets you to sort of this band of uncertainty. They do have a model discrepancy to account for the structural errors in data assimilation. And then you observe something, you have error, and somehow it combines those to give you a new starting place, and then you run them, initialize the next time step of the model from this area. So a simulation is like, you don't let the model run, you let the model go one, and then you pull it towards the data a bit, and then you let the model go, and then you keep pulling it back towards the data. And the hope is that, in principle, if the parameters were right, the model would take off on the right trajectory. And, about 14 days in certain weather conditions is what we can do for weather. So, we're moving into a phase of the talk where here's what we figured out how you could do it, and then we've actually shown that you can do it. But there's no way that we were able to do this for COVID because of the lead time. So I'm going to sell to you the idea that there's a restructuring of the way epidemiological modelling works if you want uncertainty to come out the other end. But I do want to just focus for a second before I go into this on just some of the conversations that I and other people who lead UQ have had with modelers at the time. Like this proposal, maybe there's a slide on this later, but it was, we were going to come in, do the UQ, teach all the other modelers how to do it, and then it would be there for decision makers for the next few generations. And we didn't understand that that's just not possible with these models. Now, I'm going to say you can do UQ for COVID models. You can, and people have published papers since, and I can. And we did, and that was what our initial analysis was. But you can't do it in a day. So you can't feed into decision making. So kind of what's the point? It's, well, perhaps that's a little bit hubristic. But I think those that are interested in quantifying uncertainty and say that the reason they're doing that is because it's important to decision makers need to understand that we have to fit in with the lead times of decision making. That's on us, right? Because the rest of us aren't waiting forever while we've done our analysis, and the decision makers know that, so they're going to make decisions anyway. Anyway, enough of that. Let me go on to kind of what's going on with data assimilation / particle filtering, and how we can kind of nudge the COVID state vector to where it needs to be and build in discrepancy at the same time. So, suppose Y is true COVID, space and time, and we have some observations of it, not all of it, of course. What you have is a distribution for the observations given the state, and that is something. So that was that omega I think I had on the third slide. And these types of systems are in current COVID models. The theta will be fixed, and you say that, well, if I know what the state is at time -1, I know perfectly the distribution of the next time. It's my model. My model is perfect. Okay, so that's what we do. And then you can, using that assumption, the posterior distribution, the parameters of your model given the data is some prior, and then this integral is the likelihood. You're just integrating out the truth. Don't worry, we don't need to concentrate on the mathematics too much here. That's just what it is. But solving that integral analytically is impossible. Okay, fine. And the idea of a particle filter is to estimate the integral in an unbiased way, let's say, and with low error. Now, there's loads of different particle filters. So if you're a particle filter expert, bear with me while I explain the bootstrap filter just to get concepts in place. So this is our target again, just the integral, the likelihood. And what you do is you draw m particles from this distribution. So this is the start of your simulation. So you draw like m initial conditions, let's say. And then you can weight them according to the data. So which of these, so they've all got one particular state vector, and you've got the data from that time. You can weight them according to this distribution, that's easy. You can normalize the weights, that's easy. And then you can resample according to those weights. So you can just do a multinomial resampling, that's also easy. And then, so that gives you a particular value of yt minus p for all of the different particles. And you sort of go back through this integral all the way up to present day. So at each step, you've got all the particles at the last step. You sample the one-step transition from the model, and you reweight all of them. And it turns out, by magic, that product of the average weights is an unbiased estimator of the likelihood. And you can, the proof isn't even that long. It's a sort of Monte Carlo-based proof, and it's kind of nice. So this is what some of the SPI-M models actually do. They don't calibrate, they fix the parameters, the thetas, at some values from the literature. So there's data from the Diamond Princess boat, and there was some data from China, and people produce confidence bands somehow from these parameters. You plug in the middle, and then you can do this really fancy stuff to get your model to kind of follow the data and then go off. But to me, that's still a UQ problem because the model's wrong, so I probably shouldn't do that. I should probably try and put discrepancy in somewhere. And the model isn't fast enough to do this for hundreds of thousands of particles. It's spectacularly slow. If you attempted to emulate F, you can't. So to sell that, I suppose I should say that. So MetaWards is 8,000 wards, there were 12 states, and there were 8 age classes. So that model is replicated for every age group, for every ward. The state vector is massive. So to emulate that thing, and then invert all the GP matrices is probably of the order of speed of the model. Actually, the model will probably beat us because our code isn't as efficient as theirs. So that's not a starter, but maybe emulating the likelihood, which is always 1D, is. So we'll come back to this model again to bear in mind what we're going to do. So our idea, the content of the rest of the talk, is to put model discrepancy into all of the states at the same time. Okay, so there's, yes, my model says I1 is what it is, and it depends on P in some way, but actually there's discrepancy on that. So there's some error on everything. That's the first thing to think about. So our state at any particular, so the K indexes, those different nodes, they're all the model, the reality is the model at some parameters plus the discrepancy, and there's a dependence of the discrepancy on the state and what happened before, and I'll come to why that is in a second. And we use scalum distributions for the discrepancy, which are a nice kind of discrete version of an error distribution. So a scalum is the difference between two Poissons. If you set the two Poisson parameters to be equal, the expectation is 0, so you get kind of like mean zero error thing, and the variance you can control with the choice of that lambda. So just to look at what these scalums look like, they kind of look like discrete normals almost, and you can control the size of this discrepancy. So at every state, every location, we have one of these kind of errors that sort of says, here's how much error there is allowed to be. Now, it's important because we do want some error, and we do want to recognize that the amount of error that we want is going to depend on the state in some way. So if you go back to here, I said the error depends on the state. Why would that be? Well, if I look over here, let's suppose I have 1 death. My model says 1 death at the next time. As tragic as that is, that's just talking about what the model would say. Well, how wrong could that be? Plus or minus 1 seems fair. Probably plus or minus more seems more natural. Well, let's say I say plus or minus 1. You would say, okay, 1 death plus or minus 1, so you know, is that, if that's 1 standard error, maybe it could be up to 3 deaths, it seems reasonable. You're saying that your model's okay, it's accurate enough, maybe. If I have 1,000 deaths, and then my error is plus or minus 1, you'd be like, that's a good model. That's an odd round number as well, that 1,000. We can't possibly be getting 1,000 right within 1, and yet 1, which is frequently what's happening at the spatial discretization, plus or minus 1 is, you know, it's not a small error, is it? Like it could be, there could be a death, but maybe not. Whereas 1,000 plus or minus 1, that's crazy. It's too tight. So we expect larger discrepancies as things go up, so we parameterize the lambda to grow in x. You can put any increasing function of x here if you want. And the discrepancy must be bounded. And that means that we have to derive it sequentially. Let me see if the model's coming from this. So what do I mean by that? So the discrepancy is bounded for a number of reasons. First, it can't be less than negative x. Right? Because if it's less than negative x, there are negative people in my state. So I can't have negative people, so there's already that kind of constraint going on. But if we look at that, so what we do is we start at the nodes. There's a whole theory that takes a bit too long to write out, but it's better to go through it diagrammatically to see what's going on. So you start at the end. there's a limit on the number of deaths that can happen based on the number of people that were in hospital the day before, right? So the only way to get in here is from here. So the number of new people in here is limited by the number of people in there, right? So then I sample, I get a realization of my discrepancy for here, and that tells me how many deaths are in this particular simulation from hospital. And that imposes a restriction on here, because now, not only are you bounded above by the people that were in here at the time before, you also know a bunch of them have gone into here. So there's an extra complicated bound on this one. And then when you scroll back, you know, because a bunch of people have moved from hospital into this recovery, and a bunch of people have moved from hospital into death, and you know how many people were here at the time before, that there are bounds that determine how many people can be in hospital at this state. And so it goes. So I'm not going to write out the whole algorithm for how you go back through a tree like this, but we worked it out, and it's the thing that we think is a novel contribution in this space. And so you have to have these kinds of bounds. You don't need to use the skeleton, but you certainly have to think about, yes, we have this independent discrepancy on the state, but it's not independent, it's not jointly independent. It's actually got a very complicated conditional independent structure that has to follow the graph and some sort of laws of epidemiology. If you didn't follow that argument, here's a maths version of the hospital bounds for later. I mean, not going over it now. And then when we've done that, last content slide, I think, before pictures, we're going to run the model at lots of different values of the thetas. We're going to emulate the likelihood, which is 1D, or the log likelihood in fact. And then we're going to rule out all of those values of theta that are bad. And this slide is about saying how we decide what bad means. So the idea is that there's a maximum likelihood you've seen when you have in your ensemble, and then you've got some that are millions of times less likely according to the data. So we pick a threshold essentially that says anything that's, I think it's about 10,000 times less likely than the best one that we've got so far, we're going to reject that and call that likelihood approximately 0. Obviously all the likelihoods are approximately 0 because it's really high dimensional multiplication of different probabilities, but you know, when you reweight it and so forth, that's what we're doing. Okay. So, case studies to show that this thing either works or it doesn't. We'll see. So I'm going to keep showing this model. So the first thing we're looking at is an age-structured model. So there are 8 age classes. The babies are in age class 1, the over 70s are in age class 8. And we didn't aggregate, we made it run, the whole UK is one warp. So perfect mixing everywhere, no travel. So the idea, all of these parameters are inferred by the parameters of the distribution. And so the simulation is going to see if we can recover true parameters, right? So we'll pick a true value of the parameters at random. We'll pick some set discrepancy and simulate the truth, and then we're going to see if we can recover the parameters and see what the type of inference we'd be able to show and what the type of trajectories we'd be able to show to decision makers look like. So here's the first set of results. You can see lots of plots that look like that, so just explain what's going on. You have the age classes across the top, so the babies here, the children, and it sort of goes up roughly every decade until the over 70s are in age class 8. You have all of these states, the asymptomatics, deaths in hospital, deaths in the community, and so on. And the dark blue lines are the data that we're showing. So we're only going to try and calibrate on deaths. We have 50 days for simulation. The truth is the red line, and is that visible? Red line visible? Yeah. And the trajectories, we've got slightly different shading for, pains me that this says confidence when it should say credible, but whatever. We have this sort of uncertainty band. And what we've done is calibrate up to the black dashed line, so we run the data assimilation up to there. And what's going on there is every step of the model we're adjusting with the particle filter up to the black line, and then we just run the model forward for all the parameters that are there. And we've already done the history matching in this phase. So you can see these are the parameters that our uncertainty quantification has retained. And so ideally you're sort of seeing that in all the hidden states that we're capturing the truth, which we seem to be, and that we get some nice uncertainty projections going forward in everything, which we seem to do. If we calibrate for a bit longer, so that was 50 days, if we do this a simulation for longer, 68 days, things look a bit tighter. Annoyingly, the scales adjust on these pictures, so we'll get to those, get to that when it's important. And then for the parameter inference, you can look at how well you recover things. So there's a lot going on in this picture, we don't need all of it. I had to focus on the diagonals. So here are all of the parameters, and the ones that are important to deaths are alpha 1d, which is kind of a death rate in the community, a baseline death rate in the community. There's a log linear model that increases in age, so the older you are, you start from this kind of intercept. Similar for hospitalisation, hospital deaths, and then R0 and various other parameters. And so because we're calibrating to deaths only, it picks out the death-based parameters quite well. The blue is the ones that are retained, the red was the kind of prior. And I know that the red is a spiky prior over here. That is just the prior that we had for the real simulations from the ID modelers, so we retained it for the numerical study. So it recovers the parameters related to deaths well. There are parameters that it won't recover, this system, and that happens throughout. We can add hospitalisations. So we put a blue curve here and receive much tighter uncertainty quantification. That looks larger, but the regions are narrower. And it does even better with cases. Okay, so that was the first experiment, where what we did was stuck in a seed somewhere, we had 10,000 people, it was the whole UK. Does it roughly work? Now we try the age-structured model where we have all 60-odd million people, and we try the real data to see if that works. And the idea of this experiment is to show the types of UQ that we could show to a policymaker with this system. So the idea of this, by the way, is it runs overnight. Because the particle filter, the model is running with the particle filter inside it. So for one overnight set of simulations, you get these results. In principle, it's going to take some work to get there. Okay, so here is the, so you imagine we're on the Tuesday before lockdown, we've got our last set of data, we've been asked to calibrate, we've got deaths, cases and hospital admissions, and we're asked to project forward under a few different scenarios. So we can turn that analysis around. There's the no zoomed in view, so lockdown is here. This is the real data from all the way back in January. And there's a zoomed in version for obvious reasons, just so that you can see how well the calibration does. So the calibration is okay. There's something going on with cases. We think there's too many, but it's nailing the hospitalisations. And then you can look forward, my apologies, what would happen in the pandemic 1 month ahead, and show that to a policymaker if we carried on. So here it's sort of saying up to 500,000 deaths at the outside, up to 8 million cases at the outside, and up to 1.5 million hospitalisations at the outside. And then you can have a second version where you say, okay, we're going to cut down interactions by 90%. And there's the details. And we can calibrate that again, or use the same calibration and project that forward. And that says that, well, at the outside, about 75,000 deaths, and so on. But these uncertainties, for the first time ever, have the parameter uncertainty in them, and can be kind of done instantly. They also have the fact that the model is wrong in them. So this is uncertainty quantification kind of as I know it, with those extra uncertainties added in, rather than, well, we fixed the parameters and we pretended the model is true, and here's our projection. So in principle, you could do this, and then we did it with, well, we ran up to lockdown, and then we started bringing in the data from lockdown, and this other line here is do you remember the partial unlock? Feel like you can go out dog walking with your mate and have a coffee outside and stuff. I don't know where Eat Out to Help Out is, that's probably where it is. Anyway, So you can do this for partial unlock scenarios, and kind of any time government's coming up to a decision point, in principle you could have calibrated automatically and got here. The second impressive thing about this is there are no seeds. So discrepancy allows us to run the model from nothing. No infections at all, and the discrepancy in terms of the particles, a death or well, a case will pop up through the particles, and it will be upweighted if the data says there should be some cases now. So we never need to worry about the seeding problem again, and it kind of accounts for people flying in or other processes that are bringing infections into the country that we didn't have before. They're in the discrepancy. And so we thought, well, does this actually work spatially? So can we run the model without any seeds spatially and still get back an infection? So in this particular experiment I'm going to show, we're going to fix the parameters just to show that this works. So we'll run the model, we'll know the parameters, and then we'll pretend that's the data, and then we're going to try and just get the deaths and the hospitalisations from that, and run the simulation from rest with the particle filtering to see if we get back to the truth. Does that make sense? Okay, so this is what happens when you do that. The red line is the truth, the simulation that we have with the parameters. And we run the particle filter from rest, so with nothing in it, and we assimilate these deaths in hospitals, deaths in the community, hospital cases, and hospital incidents, so that the people coming in. So that's cumulative hospital cases, but we infer the influence from there. And effectively, we recover the model perfectly, or it looks perfect. There is actually uncertainty shading there. We wanted to dig in, so that's nationally. We looked at the 5 highest regions for cases and deaths. The solid line is our simulations, and well, they're lines in fact with uncertainty, and the dashed line is the truth. So we're very, very close. It's hard to see all of these things, but we're not just getting the aggregate right, we're getting it right in space if you knew the parameters. Okay, so there's another version of this experiment, because it would be lovely to have deaths, hospitalisations, by age, by local area district, and that data exists, and then somebody pre-ruins it for you and gives it to you for the analysis. So we were assimilating death there at the right level of aggregation, the one that's in the model, but you don't get that. So what you got for SPI-M, from the people that have the data, are total deaths per lab, but not by age. So you've got the sum of all of the deaths in each local area district, but not the ages. You get the age delineated deaths, but by region, not lab. And a lab is like a super, region would be the southwest, whereas there's Bristol and Exeter, and then lots of slightly bigger ones around Devon and stuff. You get the hospital cases by NHS region. NHS regions are not the same as regions, obviously. Why would they be? And then you get the hospital incidents, so new people in hospital, by NHS region and by NHS age group, which of course aren't the same as the age groups that we report, that the ONS reports. There are only 4 of those. They sort of clump all the healthy ages, the non-children and the non-elderly, in one nice class. So if you have that kind of data, then this is the perfect model experiment. So now, there's loads here. Here's the truth, and the shading sort of shows you that we're capturing things okay, but we still miss a little bit. And then you can see the breakdown. So there's the cases by region, we're doing okay, the aggregation, cases by, so there's the 4 NHS classes, and the ages by different region, and so on. There's lots of data, but it's not going in, it's less data than before. And this is what you get. And the reason I want to show this is Pandemic Next needs to fix this. Well, I mean, or just have much more uncertainty than possible. There's no reason that we have this. Like, this exists, and then someone takes the spreadsheet and summarizes it, and then makes the error bars so big on the projections that we can't do as much as we can. We need to publish this like as a standalone. Please don't pre-ruin the data before you send it. Okay, and then finally, what happens when we go with the real data? Did we solve the exponential takeoff in London, which is down to lack of care homes in the model? We had to increase discrepancy on the elderly to account for the care homes, and we did that with parameters that are sort of tunable. Deep GP emulators, that's fine, so it works. And then I think this is the last picture slide that's worth, last of two that's worth looking at. So this is now again for the real data, no seeds, so simulation from nobody in the model. We let the discrepancy do the work. And you can see just the blue data up in London peaks up, and our uncertainty follows it and is maybe slightly too wide. And it seems to come at the expense of most of our distribution being slightly above the observations nationally to sort of account for London. But broadly speaking, it seems to be working. And then we zoomed in on the lads where all the deaths were happening, and we noticed that just in this one in London here, they're all in London in fact, but this particular one we're not capturing well. I guess these are in the tails too, which is a lot better than anything else we had before, and maybe suggests we need some more stuff on our discrepancy model. Alright, so lessons learned and the end. You could do UQ on any model. Don't let me fool you by saying you couldn't do UQ for these models. You couldn't do UQ for these models overnight. And if we're going to be able to do that, we need something new. Because during a pandemic, I mean, maybe the next pandemic models will change every day and then we'll be completely screwed. But let's hope we still get like a week. And a lot of that week is taken up by people collecting data and synthesizing it and getting it to you in some sort of clean form. So you don't have a week. You have a day, if you're lucky. You probably have 4 hours. In fact, I remember at the start of Omicron, we literally had 2 hours to say, oh, could you give us a map of where Omicron is? Like, we did some other stuff when this wasn't working, because they gave us a lot of funding to help with SPI-M, so we did try to do that. You always have a seeding problem. So not only is the model different every week, but you always have this, where is the current cases, and you have to solve that. And so this method that I showed is so nice because the emulator is always 1D, so you can automate it. You never have a complex emulation problem. It's always the same emulation problem. Okay, and I'll leave that up there because we can't do this without someone embedding it into their code. Oh, and there's references. Thank you.
Well, thank you very much. That was absolutely fascinating. An insight into the inner workings of the political brain as well. Yeah, do we have any questions about this? Shall I start? Okay, great.
So, do you need more efficient particle filters? You flashed past something on the previous slide about twisted particle filters.
Yes. So, the best particle filters we use, we could get the twisted working for some reason, one day we will. The auxiliary particle filter was what we were using for ages, but it doesn't work on the data aggregated properly. So as soon as you don't have data that's directly applicable to the states, you can't use most of the advanced particle filters anymore, which is very sad, because they're a lot better. So the problem, if you know about particle filters, is once I see deaths creeping up, the only way to get cases in is to go back 5 steps in the model and add some infection. So there's going to be a lag time, and more advanced particle filters can look further ahead and then introduce cases earlier, which is obviously better, and is stuff we've got loads on, but we haven't got working, as well as we want to yet.
Is there work being done on the opportunity to kind of create a trade-off between the compute cost of your model and the compute cost of your UQ analysis? And I'm thinking here, like, if someone tells you you've got to provide daily updates, well, you can probably run there's only one compartment in the country model and do UQ for that.
Yeah.
And so, can we tune it? Can we play with this as a parameter?
So, if it was all set up working seamlessly, I guess that would be the ideal, right? Because some decisions probably don't need spatial discretization, and some, like, where should we test and where should we lock down, and we obviously do. Obviously we're not there, because we would have to, like, we coded up a version of the model ourselves so we could invent the particle filter. This is beta. For the real models, we have to first get them to buy into the fact that there's all this uncertainty that we know how to put in that they're not putting in. And then these questions become important, I think. How do you code a framework up that allows you that kind of flexibility?
I was wondering, like, how much? So, I mean, what data do you kind of need for that? Do you need? I mean, if you don't have sort of lots of data at multiple time points, were you using? I guess you need to know the observed values of all of those health states within the model to kind of, I guess, be able to know if you're correct and the particle filter to work.
Well, I mean, you don't know all the observed states in most statistical problems, right? You know the data, you have some error on the data, and that relates to the states that you have in some way. Ideally, it's data from the state, which for COVID do exist, but not in any way that they would give you. Usually it's because of data protection, right? So if one person dies in one lab, they don't want to tell you that it was one, because then you could figure out who it was, in principle. So then, okay, so you aggregate to some level and then you lose something, but that doesn't make a difference for the method. I guess you're saying, well, how could you predict that the model's doing okay? Well, you just leave some data out. You know what the aggregation is, so then you run the model, you predict the data you left out. You predict all the relevant states and then you do the aggregation and you see if it works. But I mean, when you're actually in the pandemic doing this, you've got, well, look, it worked up to now, and that's what it says for the future, go and do something. and all the other models are doing the same thing in some sense.
Okay, well, I think in the interest of time, if anyone wants to talk to Daniel, we've got him for a few more minutes before you have to race up to your train.
I think you got me for an hour, actually.
There you go. So come and join us immediately after if you've got anything else to discuss. Thank you very much.
Thank you.